Welcome, my dear learners, for this course on tribology. Let us continue from the point where we have stopped in our previous lecture. In our previous lecture, we have derived expression for oil flow rate, that is discharge, and also for pressure distribution in an hydrostatic step bearing. Continuing from the point, in today's lecture, let me derive an expression for load carrying capacity and power loss due to friction in an hydrostatic step bearing. That is, in today's lecture, let us derive expression for load carrying capacity and later I will derive expression for power loss due to friction. Now we have to derive expression for load carrying capacity, as I already explained in our previous lecture. In case of hydrostatic step bearings, the load acting on the journal or the shaft will be withstand with the help of pressurized oil, which will be pressurized with the use of external accessories such as pump, etc. Now the inlet pressure, which is nothing but pocket pressure, which helps us to withstand the externally acting load on the journal or the shaft. So this figure is available in our data handbook. If you refer page number 24.46, figure 24.48, you will get the diagrammatic representation of hydrostatic step bearing. Now if I draw a 2D sketch of it in the top view, indicating the diameters of pocket as well as the shaft, we know that this is the diameter of pocket denoted by D1, and this is the diameter of the shaft or journal, which is denoted by D2. And let me consider an elemental ring in the oil film. Let me consider an elemental ring like this, whose thickness is dr. So consider an elemental ring having thickness dr at a radius r. Let us have an elemental ring at some radius r from the center, whose thickness is dr. Consider an elemental ring r. Let us take the thickness of which as dr. dr is the thickness of this elemental ring. Now the load whatever acts on the journal or the shaft, that is D2, will be withstand with the help of oil pressure, that is pressurized oil present inside the pocket. So therefore the pocket pressure P0 will act along the cross section of the shaft. Correct? The pocket pressure will act along the cross section of the shaft. The cross section of this pocket will be pi r1 square. That is one thing. And also the oil will be distributed over the surface of the shaft or the journal. So therefore oil is also distributed over the surface of the journal. We know that pressure which is distributed over the surface of the journal also provide resistance for the load acting on the journal. So therefore the resistance force is pressure times the area. So the surface area of the journal is nothing but 2 pi r, thickness is dr. Let me integrate it with the radius varying from r1 to r2. Radius varying from r1 to r2. This is the pressure distributed over the surface of the journal, and this is the pocket pressure. Now if I substitute the relation which we have derived in our previous lecture, that is the correlation relating pressure distribution and the pocket pressure, if I recall, we have derived the expression as the pressure distribution P is equal to ln of R2 by R divided by ln of R2 by R1 multiplied by pocket pressure P0. So therefore substitute this pressure distribution equation in equation number 1 and simplify. I will get the load carrying capacity W is equal to P0 by R1 square is the resistance force from the pocket, and we have plus resistance force from the surface area of the journal, which is given by R1, integral is from R1 to R2, 2 pi r times we have p. So that is, let me substitute the value of p. P is given by ln of r2 by r divided by ln of r2 by r1 times p naught into 2 pi r dr. So this relationship between pressure distribution and the pocket pressure has been derived in our previous lecture. Now rearranging the terms and integrating the second term in this equation, we have p naught by r1 square plus, let me take out the constants which does not contain r, that is p naught 2 pi divided by ln r2 by r1 does not contain r. We are integrating with respect to radius r. So therefore if I take out the constants, we have p naught 2 pi divided by ln of r2 by r1. I should integrate this equation from r1 to r2, that is ln of r2 by r into r dr. Correct? Now this is of the form integral of u into v. So integral of u into v is u first function integral of second minus integral of integrated second into derivative of first, right? So if I do that, what I am going to get, w is equal to p naught by r1 square plus 2 pi p naught divided by ln of r2 by r1 times first function, that is ln of r2 by r first function into integral of second. Integral of second will yield us r square by 2. Integral of r is r square by 2 minus integral of second, that is integral of integrated second is r square by 2 into derivative of first. So this is of the form log x. First log x is 1 by x. If I write 1 by x, I will get it as r by r2 1 by x times, now if I, this is of the form minus y by x. I am differentiating with respect to x, so therefore I left out with the differentiation of 1 by x is minus 1 by x square, so therefore I will get it as minus r2 by r square minus r2 by r square dr. First function integral of second minus integral of integrated second times the derivative of first. Derivative of first is this one. Log x is 1 by x and y by x is minus y by x square. Minus y by x square. Correct. So now if I simplify, I left out with this r2 and r2 will get cancelled. This r square and r square will also get cancelled. So therefore I finally left out with, so I should give the limit from r1 to r2, correct? So therefore the final answer what I will get will be p naught pi r1 square plus 2 pi p naught divided by ln of r2 by r1 times ln of r2 by r into r2 by 2. Now integral of r by 2. Integral of r by 2 is r square by 4. Minus of minus will be plus. So I left out with, we have integral of r by 2 is r square by 4. Limit is from r1 to r2. Right? Ln r2 by r square by 2, minus of minus is plus, integral of r by 2 is r square by 4. Limit is from r1 to r2. Now if I substitute the limit and simplify further, I will end up with W is equal to P naught pi R1 square plus 2 pi P naught divided by ln of R2 by R times upper limit minus lower limit. So that is ln of R2 by R2 into R2 square by 2. Let me put it like this, plus R2 square by 4 minus, so we have upper limit minus lower limit. Lower limit is R1, so therefore I will get it as ln of R2 by R1 into R1 square by 2 plus R1 square by 4. Correct? Now R2 by R2 is 1, log 1 is 0, 0 into anything is 0. So this term will become 0. So if I simplify further, I left out with W is equal to P naught pi R1 square plus 2 pi P naught by ln of R2 by R times log 1 is 0, 0 into anything will be 0. Left out with R2 square by 4, R2 square by 4 minus, plus into minus minus, I can take this as R2 square minus R1 square by 4, correct? R2 square minus R1 square by 4 and minus this term. This term is ln of R2 by R1 times R1 square by 2. R1 square by 2. Ln of R2 by R1 times R1 square by 2 minus. So this minus this, I have LCM 4. So therefore I wrote it as R2 square minus R1 square by 4. Now multiply this individually to these two terms. So I will get, if I multiply these two individually to that term, P naught pi R1 square plus, so if I multiply, I will get here 2 and here 4. If I remove that, I will get it as pi P naught times R2 square minus R1 square divided by 2 into ln of R2 by R1, sorry, R2 by R1 plus into minus minus, this term and this term will get cancelled. I left out with 2 and 2 will also get cancelled. I left out with 2 pi, sorry, 2 and 2 will also get cancelled, right? 2 and 2 will get cancelled. This term and this term will also get cancelled. I left with pi P naught R1 square. Pi P naught R1 square. So pi P naught R1 square, pi P naught R1 square will get cancelled. Now in terms of diameter, if I write, I will get the equation as W is equal to pi times P naught, pi times P naught. Here I have radius square. So radius square is nothing but diameter divided by 4. 4 to the 8. So therefore I left out with, in terms of diameter, as d2 square minus d1 square by 4. 4 to the 8. So 8 ln of d2 by d1. So this is the expression for load carrying capacity. This is nothing but equation number 24.139b, referring to page 24.47 of our data handbook. Now rearranging it, I will get the expression for pocket pressure. expression for pocket pressure will be P naught is equal to 8W ln of d2 by d1 divided by pi P naught d2 square minus d1 square. This is nothing but equation 24.139a referring to page 24.46. So this is the expression for load carrying capacity. Let me pause this video for a while so that you people can copy it down. Later I will derive expression for power loss due to friction. Now moving ahead, let us derive expression for power loss due to friction in an hydrostatic step bearing. That is the fourth derivation, that is expression for power loss due to friction. Expression for power loss due to friction or frictional power loss equation. Now to derive the expression for power loss, we have the general equation for power in terms of torque, which is given by power. Let me indicate suffix mu because it is power loss due to friction, which is given by 2 pi nt by 60,000. This you people already know. 2 pi nt by 60,000, unit will be in kilowatts. Now if I find the value of frictional torque, then I can find what is the frictional power loss. Now frictional torque can be computed as the elemental torque integrated from R1 to R2. So elemental torque delta T integrated from R1 to R2, right? Integrated from R1 to R2, what is the elemental torque? Now to find the elemental torque, we know that frictional torque is equal to frictional force times the radius. So therefore now we know that elemental torque is nothing but elemental frictional force times the radius. Elemental frictional force times the radius. Now to find the frictional force is nothing but stress times the area. Shear stress times the area. Now frictional shear stress from Newton's law of viscosity is given by frictional force is equal to, from Newton's law of viscosity, it is given by absolute viscosity times the velocity gradient or shear rate U by H. Shear stress is directly proportional to rate of shear strain, the proportionality constant being absolute or dynamic viscosity. So this is Newton's law of viscosity times the area. So what is the area of this element? Area of this element is 2 pi r dr. 2 pi r dr. Now the velocity u is nothing but what? So this is not moving linearly. The journal won't move linearly, journal will be rotating. So therefore what is the relationship between omega, angular velocity, and u, linear velocity? That you people already know, that is delta f is equal to eta. The relationship between linear velocity and angular velocity is radius times the omega is linear velocity. The linear velocity u is equal to radius times the angular velocity divided by h into 2 pi r dr. So now if I substitute this in equation number, let us take this as equation number 1, 2, this as 3, let me write it properly, 2, 3, and this as 4. Now if I substitute 4 in equation number 3. So substituting 4 in equation 3, substituting equation 4 in equation 3. So substitute equation 4 in equation 3. I left out with frictional torque delta T is equal to eta times R into R is R square into R is R cube. So I'll get 2 pi omega by H, 2 pi omega by H into R cube dr, into R cube dr. That is what I will get if I substitute equation 4 in equation 3. Now I can substitute for omega also. What do you call for omega? Omega is 2 pi n by 60, right? Omega is 2 pi n by 60. So therefore, if I substitute for omega, we know that omega is 2 pi n by 60 and n being the RPM. I left out with delta T. So let me directly substitute for equation number 2. From equation 2, I'll get the torque as torque is equal to, integral is from R1 to R2 eta times 2 pi by H into omega is 2 pi n by 60 into R cube dr, So therefore I'll get the torque as eta times 4 pi square n by 60h into integral of R cube dr. What is integral of R cube dr? So integral of R cube dr is R to the power of 4 by 4. So integral of R cube dr is R to the power of 4 divided by 4. Upper limit minus lower limit will yields us R2 to the power of 4 minus R1 to the power of 4 divided by 4. Now I can cancel these 4 and these 4. Now substitute this in equation number 1. Substituting it in equation 1, substituting in equation 1. If I substitute this in equation 1 and solve, I will get power loss due to friction P mu will be equal to 2 pi into 2 pi by 1000 I will write, and I will write it as n by 60 into torque. Torque is this one, so that is eta into pi square, pi square by h into, again I will write it as n by 60 into R2 to the power of 4 minus R1 to the power of 4. Correct? N by 60 can be written as RPS. N by 60 can be written as RPS. That is RPM by 60 is RPS, that is small n dash. So therefore I left out with P mu is equal to 2 pi square into pi is 2 pi cube by 1000 times eta, this is n dash and this is n dash, I can call it as n dash square. N dash is n by 60, n dash into n dash is n dash square, eta I left out with h divided by h into R2 to the power of 4 minus R1 to the power of 4. In terms of diameter I can write it as d2 to the power of 4 minus d1 to the power of 4 divided by 2 to the power of 4. 2 to the power of 4 is 2 to the 4, 4 to the 8, 8 to the 16 divided by 16. Right. So final answer, if I simplify, I am going to get power loss due to friction as 0.062 into eta n dash square, eta n dash square by 16h times d2 to the power of 4 minus d1 to the power of 4. This is equation number 24.141 referring to page 24.47 of our data handbook. So this is the expression for power loss due to friction. Now in examination, if it is asked to derive any of the 4 equations, that is discharge or oil flow rate through the hydrostatic journal bearing, or expression for pressure distribution, or relating pressure distribution with pocket pressure, and the third one is expression for load carrying capacity, and the fourth one is expression for power loss due to friction. So if any of these 4 derivations is asked, you should draw the neat sketch referring to page number 24.46, figure 24.48, and distort the assumptions without fail. Based on these assumptions only, we have derived these 4 relationships. So this completes the theoretical aspects of hydrostatic step bearing. In our next lecture, I will take up numerical problems on hydrostatic step bearing. That's all from this lecture. Thank you all.